Morning students, welcome back to our next class. Today's class, first I will explain one theorem. That theorem having 3 points. Either total theorem is important for long answer, otherwise individual points are important for short answers. This theorem totally having the 3 points. Okay, now I will start that theorem. See the statement one. Our theorem is let y be a subset of a Hilbert space H. Then we have to show that the following. First one is y is complete if and only if y is closed in H. Second one, y is finite dimensional, then y is complete. Third one, if H is separable, then y is also separable. See the proof now. So in this proof, first we are writing the given conditions. Let H be a, let y be a subset of Hilbert space H. Okay, only 2 conditions are given in the statement. First one is H is the Hilbert space. Second one is y is the subset of, not subset, here y is the subspace, not the subset, the subspace. Here also something, y is a subspace of H. By using this, we have to show that the conditions. First one, to show that y is complete if and only if y is closed. Okay, for this, here we are taking first necessary condition. So in this necessary condition, first suppose the y is complete. So suppose y is complete. To show that y is closed, for this purpose we are taking one element in the y bar. Let small x be an element in y bar. Then by the known theorem, what is the known theorem? In the unit 1, second topic, first theorem. So then by known theorem, the theorem having the 2 points. Now here we are applying our first point. There exists a sequence xn in y. There exists a sequence xn in y such that this xn tends to x, such that xn tends to x. Later, since y is complete, so that automatically that sequence is, this limit is also belongs to the same point. So here, by applying the known theorem, there exists a sequence in the y such that xn tends to x. Here we are applying the since part. Since y is complete, so by applying the completeness, Cauchy sequence is convergent, so that already this sequence is convergent, meaning is the sequence and this limit point both are belongs to the same set. So here sequence is in the y, so limit point also belongs to y, so that implies x belongs to y. So in the starting, x is in the y bar. Now we got x is in the y. Mean to say, therefore, x belongs to y bar implies now x is in the y. So this x is replaced with y bar, which is subset of y. Next, we have to show the remaining condition. That is, but y is subset of y bar always. we are taking one Cauchy sequence in the while. Later we have to show that Cauchy sequence is converges in the while. Every Cauchy sequence is convergent, then space is complete. So that finally we will get our required condition. So what we have to show here, every Cauchy sequence is convergent. For this purpose, we will take one Cauchy sequence xn in the y. See, now we are taking one Cauchy sequence in the y. So let sequence xn is a Cauchy sequence in y. Okay, y is already subspace of H. To say since y is subset of H, that implies subset meaning is all the elements of y are is in the H. Element of y is now xn, so that automatically xn is belongs to H. Mean to say that implies xn is Cauchy sequence in H. Okay, what is the H? H is a Hilbert space. Hilbert space mean to say complete inner product space. Mean to say since H is complete, by the definition of completeness, every Cauchy sequence is converges, so that in the H Cauchy sequence is xn, so this xn is converges to x in the H. Okay, that implies sequence xn is converges to a point, converges to a point, say x in H. We are taking that point, that's why say x in the H. Next line, since y is closed, since y is closed, by applying the known theorem, then this point x belongs to y. What is that known theorem again? Second in the unit 1, second topic, first theorem. So once this xn is closed and x belongs to y, mean to say this xn is converges to this point. Xn is already Cauchy sequence in the y, so that it is a converges to x. So finally next line is thus every Cauchy sequence in y is converges in y. So Cauchy sequence in the y converges to a particular point. That point is also in the y, so that converges in the y. So every Cauchy sequence is converges, then space is complete. Hence y is complete. This is our required sufficient condition. Finally, hence y is complete if and only y is closed. This is our required first point of this theorem. Clear now? Individual points also very important for short answers. See our next point, second one. What is our second point? If y is finite dimensional, then show that y is complete. Second point. Suppose y is finite dimensional. Okay. Then what we have to show that now? We have to show that y is complete. So here we are taking finite dimensional. So are taking certain value, that is n. So once finite dimension is there, we will say basis is exist for that set. So here y is finite dimension, so that there exists a basis for y. So we are taking that basis is E1, E2. So let E1, E2, so on En be a basis for y. Is a basis for y. So now we want to show that y is complete. So our next slide is to show that y is complete. Complete means to say every Cauchy sequence is convergent. So first we are taking one Cauchy sequence is in the y. Later we have to show that the Cauchy sequence is convergent. So here we are taking that Cauchy sequence is ym. So our next line is let sequence ym be a Cauchy sequence. Be a Cauchy sequence in y. So y is already having the basis, mean to say each element of y can be uniquely expressed as linear combination of elements of with this basis. So what is the meaning of this basis? Every element of this y can be uniquely represented as linear combination of the basis elements. So here elements of y is ym. So this ym is written as linear combination of with this basis elements. That is our next line. So next line is then every element of in ym can be uniquely expressed as linear combination of basis elements. So next line is ym is equal to alpha 1m E1 plus alpha 2m E2, so on, plus alpha nm En. So this is the linear combination with the elements. So same thing can be written is in the summation form. Ym is equal to summation j is equal to 1 to n alpha jm ej. Okay, clear Amma? How to write the elements? So in the second one, only based on the finite dimensional. Finite means to say we are taking certain value, that is n. Later dimensional means to say basis exists, so we are taking n E1, E2, so on, En be a basis. Later we are writing our aim. For this aim we want one Cauchy sequence, that's why we are taking Cauchy sequence. Later by applying the basis definition, every element of y can be uniquely expressed as linear combination of its basis elements. Linear combinations are the scalar into element. So here alpha 1m, alpha 2m, all are the scalars. Now this can be represented in the summation form. Summation j is equal to 1 to n alpha jm ej. See our next line. In the next line, we are using the Cauchy sequence definition. So our next line is, since ym is a Cauchy sequence, definition of Cauchy. So that is, for each epsilon greater than 0, there exists a natural number capital N. There exists a natural number capital N greater than 0 such that norm ym minus yr is less than epsilon for all m comma r greater than or equal to capital N. This is nothing but the Cauchy sequence definition. So our next line is, therefore write this condition reverse. Epsilon is greater than norm ym minus yr. Okay. So in this in our next line we have to substitute in place of ym value in terms of the summation. So what is the ym? Summation j is equal to 1 to n alpha jm ej. So write it ym value summation j is equal to 1 to n alpha jm ej. Similarly, based on this, we have to substitute yr value. Yr means to say in place of m, what we have to write? R. So summation j is equal to 1 to n alpha jr ej. Okay. Now we have to take the common here summation and the ej terms. So summation j is equal to 1 to n, and even ej also we are taking common. So remaining terms are alpha jm minus alpha jr. Okay, and that are norm. Now norm a into b formula we have to write, then which is greater than or equal to here not the norm AB formula. Here we are using linear combination theorem of unit 1. By using that theorem, our next line is, which is greater than or equal to summation j is equal to 1 to n modulus of alpha jm into alpha jm minus alpha jr into constant c. So here which theorem we are using? Linear combination theorem of unit 1. Clear? By applying that theorem statement, this entire thing is greater than or equal to summation I is equal to 1 to n modulus of the constant, modulus of the scalars into certain constant. This entire thing is true for all n greater than, for all n comma r greater than or equal to. So here we are writing for all n comma n greater than or equal to r. Even for the next lines also we have to write for all m comma r greater than or equal to n. Here also same thing for all m comma r greater than or equal to n. Even for this one also for all m comma r greater than or equal to capital N. Okay, now clear? Now we are writing this condition reverse. Okay, see the next line. See the next line is now. We have to write this condition is reverse. Okay, write it reverse first. Summation j equal to 1 to n modulus of alpha jm minus alpha jr into the next line, we have to eliminate the summation and write, that is modulus of alpha jm minus alpha jr, which is less than or equal to epsilon by c, eliminating the summation. That's why here we are writing for j is equal to 1 to so on n. Instead of writing the summation, we are representing the values r in terms of the words for j is equal to 1 to so on n. So now if you are observing this scalars is values, distance of two scalars is less than or equal to certain constant, and here these are the sequences. So two sequences value is less than a certain constant, then one is called Cauchy sequence. So that here, therefore alpha jm is a Cauchy sequence in either R or C, either real numbers or complex numbers. Since R and C are complete, so that it is convergent also. Since R or C is complete, so that the starting point, it is a Cauchy sequence in this basis, right? So maintain the same basis, so that the sequence alpha jm is convergent. Okay, now? So it is convergent, we will say limit point exists. Now we will take that limit point is alpha j. Okay, now? See, from this video only you can copy the notes. Okay, listen carefully and copy it. See, now we have to take that limit point is alpha j. So our next line is, let alpha j be the limit of Cauchy sequence alpha, Cauchy sequence alpha jm. Okay, alpha jm. Next we are taking y value. This is the sequence, so that keep in the places. Okay. Next take one point y. Let y is equal to linear combination of the basis elements. So let y is equal to alpha 1 e1 plus alpha 2 e2 so on plus alpha n en. Later observe this one. Clearly this element belongs to capital Y, because every element can be represented as linear combination of the basis segments. So here these are the linear combination of basis. Basis is for y, so that this small y belongs to capital Y. Now we have to calculate norm ym minus y value. Now norm ym minus y. So from the above lines, norm ym value we have already in terms of the summation. So summation j is equal to 1 to n alpha jm ej. Similarly, from this y we have to write y value in terms of the summation, just alpha j ej. Here also same thing, take a summation and alpha j comes common. Summation j is equal to 1 to n alpha jm minus alpha j into ej. Okay. Now here we have to apply norm alpha x formula. Norm alpha x is equal to in instead of the norm alpha x, simply we have to take norm of a into b. Norm of a into b is less than or equal to norm a into b. So norm of constants, we have to take modulus also for this. So modulus of alpha jm minus alpha j into norm ej. Okay. Next line is from the above line alpha jm tends to alpha j. So write the next line, since alpha jm tends to alpha j as m tends to infinity. Now if we are substituting this value in the above lines, then above line becomes norm ym minus y tends to, in place of alpha j, what we have to substitute? Alpha j minus alpha j goes to 0. So above line becomes norm ym minus y tends to 0 as m tends to infinity. Mean to say ym tends to y as m tends to infinity. Therefore ym is converges. So in the starting lines we took ym is a Cauchy sequence. So every Cauchy sequence is convergent. Mean to say the space y is complete. Okay. Right. See our next lemma substituting this value. Then our next line is norm ym minus y tends to, so in place of alpha j, substitute alpha jm, substitute alpha j, then alpha j minus alpha j becomes 0. So that it tends to 0 as m tends to infinity. Mean to say here ym tends to y as m tends to infinity. So that is sequence ym is converges to y in capital Y. That's why in the previous lines we already have small y belongs to capital Y. So in the starting lines we know that we are having ym is a Cauchy sequence, so that this y, every Cauchy sequence is convergent. Mean to say space is complete. So our next line is hence y is complete. This is our required second bit. Okay. Later I will explain our third bit. Right now our third bit is, suppose h is separable, we have to show that y is also separable. For this, h is separable. Separable means to say it has a countable dense subset. So then there exists a countable dense subset m in h. That is, m is countable. Dense means to say its closure is equal to h. So m bar is equal to h. Next, m bar intersection y value is equal to m bar equal to h. So h intersection y, in this intersection is the small set, that is the y. Okay? Right. Also m is subset of m intersection y is always subset of m. See these conditions. A intersection b is always subset of a, and a intersection b is always subset of b. Same thing, m intersection y is subset of m. Also m bar intersection, here m intersection y whole bar we are taking. Y is closed so that y bar is equal to y of m. Then m bar intersection y is closure of m intersection y in the set y. Now to show that m bar intersection y, sorry, m intersection y whole bar intersection y is equal to m bar intersection y. For this purpose, m bar intersection y is subset of m intersection y whole bar. Same conditions we have to apply. Now write it in bar separately, m bar intersection y bar. Again, this m bar intersection y bar is subset of m bar and y bar. Take it as So what we got? M intersection y whole bar intersection y is subset of M bar. Next time, this M bar, M intersection y bar intersection y is subset of y bar. Y is closed, so that y bar is equal to y. This is our next leg. M intersection y whole bar intersection y is subset of y. Now y is equal to, from the above line, M bar intersection y, substitute that term in the next line. Take the equation number 1. Next time we have to show that the M bar intersection y is subset of M intersection y whole bar intersection y. For this purpose we are taking one element in the set. Let x belongs to M bar intersection y. One element is in the intersection, mean to say that element belongs to the first set and second set. So let x belongs to M bar and x belongs to y. Since M bar is equal to M, so that the x belongs to M and x belongs to y also. Now this box part is a since part for your understanding purpose. No need to copy in the notes. Okay? This is only the actual part, definition of the theorem. Now here we are taking this since x belongs to M bar intersection y implies there exists a sequence in the M intersection y. Sequence x and intersection y is a sequence in the M intersection y converges to this line. If you are applying here, you will get this line. See what is the since part? X belongs to M bar. Then if and only if there exists a sequence in the M such that that sequence is converges. So same thing here, x belongs to M bar, this intersection y is common. So automatically there exists one sequence in this M. So sequence x and intersection y is a sequence in the set M intersection y converges to x M. And we already having x belongs to y also. Okay, right. Now x belongs to y. From this implies that this element x belongs to. So apply this if and only x belongs to M bar. Here M bar means the sequence is M intersection y whole bar. So x belongs to M intersection y whole bar, and so that intersection x belongs to which one? Y. So what we got here, therefore x belongs to M intersection, x belongs to M bar intersection y implies x belongs to M intersection y whole bar intersection y. Now this set x is replaced with this set, then subset of second one. This is equation number 2. From 1 and 2 both are equal. So now here we are getting the conclusion. Therefore M bar intersection y is closure of M intersection y in the set y, where M intersection y is separable and M intersection y is subset. So this one is a subset of M bar intersection y is subset of M intersection y. This is the separable. Then automatically M bar intersection y is also separable. All these are in the set y, hence y is separable. This is our required third point. So with this theorem, our topic is completed. Okay. With next topic, we'll meet you in the next class.